Welcome everyone to this week's Autonomy Talks. This week is a great pleasure to have with us Dr. Juncal Arbelaiz, who is a Schmidt Science postdoctoral fellow at Princeton with the Mechanical and Aerospace Engineering Department and the Center for Statistics and Machine Learning. So something about Juncal: previously she received her PhD degree in applied mathematics from MIT, actually in September 2022, so recently. And her research interests are in optimal decentralized control and estimation of spatially distributed systems. As you can see from the biography I sent you, she received a number of awards for her work. The recent one is she was honored to be a rising star in electrical and computer science in 2021. And today she's going to talk about distributed Kalman filtering for systems with spatiotemporal dynamics. I'm personally very interested in the subject, and so I give you the stage, Juncal. Go ahead.
Okay, thank you very much, Joel, for the invite and for the nice introduction. So as Joel said, I'll talk about some of the work that I did during my PhD. And so the idea for today would be to look at systems with simple spatiotemporal dynamics, so mostly systems described by PDEs with some shift invariant symmetries. And what I will try to show you is that the Kalman filters have very nice structural properties that we can actually exploit to design distributed versions of this Kalman filter. So to start the talk, let me give you a little bit of motivation of where this work comes from. So early in my PhD, I became interested in soft robots. This is this new trend in robotics, bio-inspired robots, in which we are hoping to be able to exploit or harness this additional flexibility to achieve things that traditional robots cannot do. So for example, this would be very useful for things like human-robot interaction. You can think in medicine, the possibility of introducing a small robot inside the body that could safely interact with tissue, or even having a robotic patch that you could add to a sick heart to help this heartbeat. Now, we are also seeing the possibility of increasing the number of sensing that we are embedding into these systems, which is good for state estimation, but these two things combined together also bring some system theoretic challenges. So the first one is that these systems are described by partial differential equations. These are systems that we say that have an infinite dimensional state. So the math to design, let's say, optimal controls or in general controllers and estimators for these systems, it's a little bit more challenging than in traditional finite dimensional settings. And then if to this we have this high number of sensors, that in principle is something good to estimate the state of our system, but taking into account that we may have limited onboard centralized computation, this can also be a bottleneck. So we are left with this question of how do we address these two challenges, the infinite dimensional state of the system and the need of processing all this sensory information. So given that these are bio-inspired robots, early in my PhD, the question that I ask is how do actually biological systems handle all this? So I'll give you a few examples that I think are pretty cool. So one of them is worms, actually. So how this thing locomote is through the use of peristaltic waves along the body. These are local contractions and expansions of the body that are coordinated to produce a wave, a peristaltic wave. And recently it was shown by some physicists at Harvard and some neuroscientists that actually local coordination so local information exchange is sufficient in order to sustain these waves. So pretty much if neurons are distributed along the body, if these neurons have only access to local strengths, this is sufficient to propagate these waves. Another very cool example is the jellyfish. So the jellyfish doesn't have anything close to a centralized brain as we think about it. So actually they have two nervous nets distributed along the body. And with this totally distributed architecture, they manage to locomote and they manage to feed and they manage to hunt. So it's a pretty cool example of, I think, distributed control and information processing. And finally, maybe another example that you have heard of, it's the octopus. So in this case, we do have a central brain, but actually 2/3 of the neurons are distributed along the body. So it is known that each of the tentacles has some degree of autonomy, for example, to do exploration of the environment. So in the words of Wells, not mine, the point that I'm trying to make here is that in a very flexible animal, motor control must of necessity be hierarchical and proprioceptive information must be utilized locally, a condition perhaps common to all animals that lack jointed skeletons. So proprioceptive inputs probably never penetrate to levels of the centralized nervous system. And what I mean by proprioceptive information in this context is really sensory measurements. And this idea of locality, you'll see that it will actually play an important role in all my talk. So another question that I became very interested in is, so on top of this, we observed that these decentralized or distributed architectures work very well in the presence of noise, both sensory noise, but also environmental noise or stochastic perturbances in the dynamics. So actually, I extracted this quotation from a paper, and I'm seeing like Corentin Brayat here right now. So now I know I'm excited because it's a paper by Corentin and Mustafa Kamash. That says that living organisms have learned to rely on noise and uncertainty to implement certain functions that would have been difficult or even impossible otherwise. So a question that I became interested in is, what is the role of this sensory and this environmental noise in either fostering or not fostering, we don't know, this sensory feedback localized architectures, okay, in a space. So for this talk, most of the talk will be about this interplay between the noise and the spatial localization of sensory feedback, okay? And in particular, I will be focusing just on the optimal state estimation problem. And I will be talking about Kalman filters, so a pretty standard framework. So there are 3 questions that I will be trying to answer today. The first one is, in this kind of systems with spatiotemporal dynamics, do we observe some peculiar spatial localization property in this Kalman filter, which would mean that I mostly rely on local sensory information exchange in order to do a state estimation. The second one is, what is the role of noise in this spatial localization? Do we observe that noise actually fosters the spatial localization? So kind of distributed architectures, or do we see that noise actually enforces global information exchange or fosters global information exchange? And the final question would be, once we understand these information structures in a centralized setting, how could we utilize this to design architectures that are actually decentralized? Okay, so this is more thinking about applications, like for example, if I were to design a soft robot. So since we will be answering these questions in the context of Kalman filters, what I will show you today is that we can actually equivalently frame these 3 questions in the Kalman game. So pretty much it will be about trying to derive some properties of the Kalman game in this setting. So the first one is really going to be about, could we prove that the Kalman game is spatially localized? The second one, so just to give you an example of, or a graphical, I would say, representation of what this means. What this means is that if I have something like this worm or a soft robot where I have distributed sensing, here represented by all these white dots, and if I want to do a state estimation at a particular location X, this question about locality has to do with, do I really need to gather all these measurements and send them back to this position X in order to do a state estimation, and are they all equally weighted, so equally important, or could I instead show that in order to do a state estimation at X, I mostly rely on local information, and as I go away or I depart from X, the importance of these measurements decays. So the second one is going to be about the role of noise in this localization of the Kalman game. So the idea is that if I manage to establish that my Kalman game is spatially localized, do I observe that noise is actually fostering more localization, or does it have the opposite effect and make my architecture be more global or more centralized? And then finally, the idea is, now that we understand, or hopefully we'll understand the spatial structures of these architectures, how do we impose spatial locality constraints on the Kalman game? So what this would mean is that if I manage to establish that my game decays in a space, how could I come up with a framework that would allow me to design a filter architecture where, in order to do state estimation at a particular location, I only use a few of these neighboring measurements? Okay, how could I enforce this? So I divided the talk into 2 parts. The first part will really be about the structure of the centralized Kalman filter, and some of the proof techniques will rely on this paper that I cite here on distributed control of the spatial invariant systems. I will really not go through the proofs today. Rather than that, I will just try to give you the high-level intuition of where the results come from and how to derive the results. And then once I manage to establish what are the structures of this filter, what I will do is to use this to inform this decentralized architecture design. Okay, so let's start with part 1, that is about what are the information structures of the centralized Kalman filter in this setting. So the plant that I will be looking at has this form. So this is pretty standard. we assume that we have some state that evolves both in a space, noted by the coordinate x here, and in time. We assume that the dynamics of our system is perturbed by some environmental noise that we note by W, and that my spatial domain is going to be the whole real line. Okay, so just to keep things simple, I'm looking at 1D, and you can think of this as having the limit of, for example, a very long worm or a very long tentacle. Regarding the measurements, I will assume that these measurements are spatially distributed. So keep in mind this sketch that I showed you of the worm, where the measurements were collected along the whole body. And we'll assume that measurements are also corrupted by noise. So for both of these noises, the assumptions are the standard. I will assume that they are spatiotemporally wide, Gaussian, zero mean, and independent from each other. So I introduce a notation now. I will use this bold font to denote signals that are distributed in a space. So each time that you see this bold font of whatever T, what you can think of is that this is going to be a spatially distributed signal, okay? And furthermore, for this talk, I will assume that all my signals will live in L2, in a space. So with this notation, what we can introduce is the abstract, what we call the abstract state representation of the plant. So this is just writing the plant as if it were a finite dimensional system, just taking into account that actually each of these signals lives in an infinite dimensional space now in L2. And what I will further assume for this talk is that these two operators here are spatial invariant operators. So this pretty much means that there is a shift in variance in the spatial coordinate. So for example, differential operators, that is what I will be focusing on today here for A, or spatial convolutions are operators that satisfy this assumption. Okay, so what the spatial invariance gives me is that it allows me to define the spatial Fourier transform in this way. So each time that you see a hat, it means that I'm working in the Fourier domain, and this lambda will be used to denote the spatial frequency. So if we take the Fourier transform of my whole plant, what I observe is that I actually can get a decoupled family of ODEs, where we use this notation A hat of lambda and C hat of lambda to denote the Fourier symbols that are just multiplication operators, given that these were spatial invariant operators, so some functions of lambda. Lambda here lives in the real line, and the interesting property is that all these systems are decoupled now. So you can really think about this plant as a family of decoupled systems in lambda, where at each lambda I just have an ODE that is describing my dynamics. So we will see that this property of modal decoupling will be actually super useful in order to get insights about what is the structure of my filter and how to design distributed filters later on. So once I have my plant set up, let's look at the optimal state estimation problem. So this will be pretty standard as well. So I define an estimation error here as between my state and the state estimate that I want to produce. So I will denote the state estimate using this tilde. And the idea would be that I'm trying to design the state estimate to be causal and to minimize the steady state variance of estimation error. So if we do that, we know that we obtain the Kalman filter, so I will not go through a lot of details, but the idea again is here, this is now a distributed parameter Kalman filter. So if this originally was a differential operator, this will be a differential operator again. And then I'll show you a bit later that it's actually an integral operator. So this is some kind of integral differential equation. So a way to interpret this is that we'll have some prediction term, a copy of the dynamics. We have a correction term that is pretty much doing feedback on the measurement error, measurement estimation error through this operator L. And this operator L is what we call the Kalman gain operator. So we know how to obtain L just from the optimality conditions. It's given by this formula over here. We also start to denote adjoint operators, and B here denotes the covariance operator of the measurement noise. And P is just the steady state covariance of the optimal estimation error. So how to obtain P? Well, is just this, as happens in the finite dimensional setting. This is given by an algebraic Riccati equation with a twist now that this is an operator Riccati equation. And since we are working in L2, so these inner products here are taking over L2. So what one can show in this spatial invariant setting is that the covariance operator P, it's a spatial invariant itself. And what this means is that all the operators that enter my equation in here are spatially invariant, and hence I can apply the Fourier transform that I showed you earlier and apply Parseval's identity in order to write the same equation equivalently in the spatial frequency domain. Now in terms of the Fourier symbols of all these operators, okay? This is why you see all these hats appearing in here. Now, under the further assumption that the domain of my adjoint operator is dense, which will happen, for example, we are looking at differential operators. What happens here is that actually this equation decouples. Okay, so what we have is that this product of the Fourier symbols over here has to be 0 pointwise in lambda. So this idea of modal decoupling again proves to be very useful because now allows us to solve this Riccati equation in closed form. If we assume that we are looking at PDEs where the state at a given spatial location x and t is a scalar, this means that I can just solve for the power spectral density of my estimation error in closed form. And from there, I can obtain the Fourier symbol of my Kalman gain, okay, in closed form. So this is interesting because it has two important implications. The first one is that the Kalman gain, L, is a spatial convolution. So the way to see this is that the gain is just a multiplication operator in the frequency domain. So when I take the inverse Fourier transform and apply the convolution theorem, this just gives me a convolution in a space. And the second one is that since this operator is a spatial invariant, the whole filter itself is a spatial invariant, which means that we are sort of implementing the same filter architecture at every spatial location X. So what is important to understand now, spatial locality, is that ultimately I'm interested in understanding how the measurements have to be a change between the different locations in my system or in the robot, in the body of this robot, in order to do state estimation. So what this means is that I really need to understand the spatial localization properties of this operator L of the Kalman gain, okay? So in particular, I'm going back to this sketch of the worm that I showed you earlier. If I look at the kernel of this convolution, and this kernel is fat, colloquially speaking, a very wide spread in a space, what this means is that in order to do estimation at X, I more or less need all the measurements, and they will be equally weighted, so they all will be important, and my filter will be quite centralized. But if I manage to establish that this kernel actually decays fast in a space, this would mean that mostly neighboring measurements are important to the state estimation at X. So this would be pretty convenient. And it would mean that my filter, even in a centralized setting, has quite an inherent degree of spatial localization. So the question is, well, all that I managed to get so far is the Fourier symbol of this gain. So I have an expression for this gain in frequency, but I want to understand physical properties of this gain. So I want to understand spatial properties of this gain. So how to do that from the Fourier symbol? Well, for particular settings, if you plug in the particular operators in your dynamics, you could always take numerical brute force inverse Fourier transforms and see how this kernel behaves in a space. But maybe there is something a little bit better or more general that we could do. And that's indeed the case. And I will show you now how you could compute spatial properties of this operator from its Fourier symbol. So the idea is that we will use something that is called the Paley-Wiener theorem, okay? So the Paley-Wiener theorem tells you that if you can define an analytic extension we denote by L hat of C of this L hat of lambda, so C here it's a complex number, and this extension is analytic in some strip along the imaginary axis when this gamma here is just an open interval. And within any compact set containing this interval, you can show a polynomial growth bound or your analytic extension. Then what you can prove is that your gain decays asymptotically exponentially in a space. Okay, so this would mean that you have a fast spatial decay. And the decay rate will be determined by the width of this analyticity strip. So I know that this is a little bit technical. So what I'll try to do now is to give you a bit of intuition about with an example about how you compute these things and how you compute the decay rates. But first, let's remember that I was also interested in understanding how the noise affects the localization of my filter, okay? So that question is equivalent to saying, how does this theta that is dictating the decay rate of my gain actually depends on noise? So if we further assume that we have we are pretty much measuring the state, but the measurement is noisy, so let's take C2 with identity, then this is the expression for my gain, for the Fourier symbol of my gain. And what I can do is to define the extension to the complex plane. So since we are working with differential operators, this term over here would just be some polynomial in C, that is now a complex number. Oops, sorry. And the second part in here will be just a square root of some rational function of C, that if furthermore we have white noises, then it would just be a polynomial. So it will be easy to show that this satisfies some kind of polynomial growth bound. So this condition is very easy to check. So now what we will need to show is that it is actually analytic in some strip and be able to compute that strip to determine the decay. So this function here is entire, so analytic in the whole complex plane, polynomials are entire, so this gives us no problem in terms of evaluating decay. But this function over here is a square root, And we know that the square roots are actually multivalued functions in the complex plane. So it means that we will need to determine the branch points of this square root in order to determine what is the analyticity region of my extension, okay? And the way to do that is pretty much to find the zeros of this polynomial, the roots of this polynomial, and we'll see that their noises actually play a role in determining where those zeros are. So indeed, the decay rate of my Kalman gain is going to depend on the noise properties that I have, of the noise statistics that I have in my system, okay? So since this is a little bit abstract, let me give you a simple example of how you go about performing this kind of computations. So we can evaluate a diffusion process over the real line. So the only parameter here is kappa, that is a diffusivity constant. And I know this is a little bit far from soft robots, but the idea is that you could do the same thing, for example, for the elastic wave equation. So I'm just picking this example because it's a little bit simpler. So what you can do is to get the symbol of your Kalman gain from the Riccati equation, as I showed you earlier, where this lambda square over here comes from the fact that we have a second order differential operator here, and then sigmas denote the variances of the respective noises in the process and measurement noise. So this function has as domain the imaginary axis, okay, in the complex plane. So what we will do is to define now the extension. So the idea is that from the imaginary axis, you extend the definition of this function towards the complex plane. And the task is now to determine where is this extension analytic. So to do that, as I mentioned earlier, you compute the branch points. So pretty much the roots of this fourth order polynomial, and this is how they look like, the finite roots. And from here, by doing some dimensional analysis, what you can actually establish is that this ratio that appears in the roots has units of 1 over length. So this allows us to define a characteristic length scale in this system that I will denote by L star in this way. So it has to do with kappa, the diffusivity constant, and also with the level of noise or the intensities of the noises that you have in your system. So if we use this L star, we can write our branch points more compactly, and we can explicitly obtain what is the decay rate of my Kalman gain. So you can see that the Kalman gain is going to decay inversely proportionally with this L star. So this decay rate is just given by the real part of these branch points, okay? So to give you a bit of intuition, you can plot these branch points in the complex plane for L star equals to 1, and this is how your 4 branch points would look like. And then the analyticity strip is the region of the complex plane that lies in between these branch points, so it's given by this area shaded in red in here. So the decay rate is just given by the real part of these branch points that we denote by theta, okay? Now, the interesting observation is that your branch points more generally are parameterized by this L star. Okay, so as you change L star, your branch points will have some trajectories in the complex plane. So what this allows me to do is to define the branch points locus. And so I did this in analogy with the root locus. The idea is that the root locus, very used in control theory, gives you insights about the stability of a linear system just by looking at the trajectories of some poles based on parameters in your system. So here we do the same, but what we would like to do is to look at the trajectories of the branch points in the complex plane instead, and rather than working with temporal frequency, we're working with a spatial frequency, okay? So what we observe is that if I start with low values of L star, I'm around the dark region of these trajectories. As I increase L star, my branch points become closer and closer to the origin. Okay, so if I plot the corresponding kernels of the Kalman gain here to the right, what it means is that when L star is small, where I have its kernels that are quite concentrated in the space. So this would mean that my filter is actually quite localized in the space and is mostly relying on local information. But as I increase L star and I go towards the origin, my analyticity region will be becoming smaller and smaller. So my decay rate is smaller, which means that my kernel becomes more widespread in the space. So I need more communications or to gather information from farther away in order to do filtering at a particular spatial location. Okay, so here the branch point locus looks very simple. This is pretty much because L star is only changing the modulus of these roots of these branch points, but not really their phase. But you can have more complicated geometries of the branch point locus depending on the dynamics of your system, or for example, having noise correlations. So in a case in which you have noise correlations and still have a diffusion process, this is how your branch point locus would look like. And this would be for a different dynamic. This is for Swiss-Hohenberg equation. So definitely your branch points could be changing phase at the same time that they are changing their modulus. So the takeaway message here is that we can use this characteristic length scale that we define from dimensional analysis as a proxy for the spatial spread of the Kalman gain. Okay, so as a proxy about for how useful measurements from far away in space are in order to perform my filtering task. So in particular, when this L star is high, we will have, colloquially speaking, these fat kernels, in which I really need to gather information from far away in order to filtering. But when L star is low, I will be in a setting in which my kernels are fit, colloquially speaking. So I'm pretty spatially localized, and I mostly rely on local information in order to do filtering. So note that the noises are tuning, okay, the degree, this degree of spatial localization or this characteristic length scale. So in particular, if I have measurements of very good quality, I will be pretty localized in the space. So this makes sense because in the limit, you know, when your measurement noise goes to 0, if you were to have perfect measurements, then you don't need to look farther away in order to do estimation. You just have a very good measurement. If the opposite thing happens when you distrust your model, so you have high measurement noise, then you also become more localized. So what the intuition behind this effect is that if you are not trusting your model, so if you think your model is of bad quality, then there is no point in looking far away because measurements from far away matter little. And then if you distrust your model, then pretty much they give you nothing for your filtering task. So you must just rely on local information and you will be doing as well as if you were looking at those measurements. So again, similar results can be extended to other kinds of PDEs. So for example, to elastic wave equation, that is more relevant for soft robots. Some further technicalities are needed because we will need to be working in so level space and so I will not cover this today, but one can similarly use dimensional analysis and this kind of characterization in the parameters to analyze the locality of the filters in that setting. Okay, so far, what I have established is that in this spatial invariant setting, the filter itself is a spatial invariant, that it is described by a spatial convolution, and furthermore, this convolution is spatially localized with a asymptotic decay rate that is exponential, actually. So with this, we answer the first of the questions that was about locality in filters. So do I really rely on local information in order to do filtering? So the answer is yes. And as a byproduct, we also show that noise is tuning the spatial decay rate of this Kalman gain, which means that effectively noise is telling me from how far away do I need to get measurements in order to do filtering. So now the question that is left to prove or to show something about is the third question, that is, how can I use these insights about the locality of the centralized architecture in order to define Kalman filters that are information constraints or where I impose certain locality requirements in a space. Okay, so what I have shown so far is that optimal ones in the Kalman filter look like that. So they have fast spatial decay, which means that at x0, I mostly rely on the measurements that are close to x0 in order to do the state estimation. But even though this thing decays exponentially, I really need to gather information from my whole spatial domain in order to do estimation at x0. So this is pretty heavy in terms of complexity and in terms of the measurements that I need, but of course will give me the best possible performance under the assumptions in this problem. Instead, what we may want to do is to design a kernel for this Kalman gain that is compactly supported, okay, where this T parameter that appears here is a design parameter that I will be imposing, so I can choose as a designer. And what it's saying is that in order to do a state estimation at a particular location x0, I can only have access to measurements up to a distance t in a t neighborhood, okay, of x0. So of course this will have less complexity in this case, but it will also have worse performance, the filter, okay? So there is this complexity performance dilemma that is very well understood as well in the context of decentralized control of distributed systems. Well, more than well understood, I would say well known, not so well understood. So the main idea here is that in order to design a decentralized or distributed filter, what we will be doing is sort of to copy the architecture of the original filter, okay? But with the only difference that my feedback operator or my Kalman gain now, rather than having this kernel that is decaying exponentially, I will try to design a kernel that is compactly supported, okay? In this between minus t and t. So the idea is that I will enforce this operator still to be a spatial convolution. So the dynamics of my filter will still be a spatial invariant. The only thing that will be changing is the support of that kernel. So the question is now what I can do to design this kernel. So previous approaches in the literature, the thing that they have been trying to do is simply truncate the tails of this kernel. So you can establish that if you don't truncate too much, so if this T is not too small, you can still preserve the stability of your filter and perform more or less decently. Now, the issue is that if you truncate too much, for example, you might be going to an unstable setting in which there could be some kernel at the same truncation level that could actually give you stability. And in general, just by truncating, you will not be having the optimal performance, okay? You will just have a stabilizing filter. So the idea here is that what we will try to come up with is an optimization problem that would allow us to select the shape of this compactly supported kernel optimally, okay? Now, these kind of problems are sometimes a little bit tough. So let me now zoom out and explain a little bit why these problems are in general quite challenging. So the issue is that both in control and in estimation, when we try to write the whole control estimation problem in the gain, these problems are actually non-convex, okay, in the gain. So this can happen even without a structural constraint. It's not a matter of trying to add a structure in your gain. It's a matter of framing the problem in the gain. So what happens is that in general, your cost function becomes non-convex, and the feasible set, so the stabilizing set of gains, can become non-convex as well. And indeed, it can have an exponential number of connected components, which is a little bit nasty. Especially if you are trying to solve this problem using things like gradient descent, where then it would matter in which part of your feasible set you're initializing your algorithm. So what has been the approaches in the literature so far? Well, for the centralized setting, we know that there is a change of variables, of decision variables in the problem that we could make that gives us an exact convexification of the problem. Okay, so this gives us an exact convex formulation. So this would allow us to remove the gain from that problem, solve the problem in the alternative variables, and then once we get the optimal value of these variables, recover the gain from there. Additionally, and more recently, it has been shown that the cost function has an interesting property that is called gradient domination, or the PL condition in the LQR problem. So the idea is that even though your cost is non-convex, just by following the gradient, it happens that you arrive to the globally optimal gain. Okay, so this is a pretty nice property that now we are seeing actually a bit of an explosion in works related to policy optimization from different groups trying to establish what are the properties of the landscape of this problem and the feasible set and so on and so forth. So what is the issue then with trying to design a structure gain if we seem to have some nice approaches that will allow us to exactly convexify this problem or to arrive to global optimality? Well, the main issue is that when you have structural constraints in your gain, these constraints in general do not propagate to these alternative decision variables that you could define. Okay, so you are pretty much stuck with the gain being your decision variable, which means that you are stuck with a non-convex problem. Okay, so what are the approaches that we have seen in the literature so far to try to handle this non-convexity? Well, mostly there are two different ways. One of them is, yes, let's try to focus on particular classes of systems that have some peculiar property that maybe you could exploit. So for example, quadratic invariance or nested systems in order to arrive to convex formulations for this decentralized problem that are actually exactly convex in the gain. The other approach is, okay, we understand this problem is non-convex, we accept it, we try to just define convex relaxations. So the idea is that you would define some relaxation to the problem in which you would obtain a gain that satisfies whatever structure you want that is stabilizing, but in general will not be globally optimal for your original problem. So there are several approaches that have been suggested in this regard. So for example, sparsity promoting optimal control. Now going back to the problem here, we actually have a lot of structure, okay, in this problem, because we are assuming this shift invariance in the spatial coordinate. We are working in L2 spaces, and then we have this additional assumption of having a scalar value of our field that we're trying to estimate at each x and t. So the idea here is, okay, let's try to write down the optimization problem for my structure gain, and let's try to derive its properties. And from there, we can see whether non-convexity arises somewhere, and if we have non-convexity, which kind of non-convexity it is, and what we could do about it. So in words, or to give you an intuition on what is the problem that we are trying to solve, it would look like that. So we are trying to find a kernel, LT, okay, that minimizes the variance of my estimation error asymptotically. So now I use this E sub t, the t, to indicate that now this will be dependent of the value of this parameter t that I choose. And the estimation error dynamics are just close to the Kalman filter dynamics, with the exception that now we will have a kernel that is compactly supported in this operator. We must have a closed loop that is exponentially stabilizing, so we will have that additional constraint. And we want the support of this LT to be between minus t and t, okay? Now, the idea here is that, well, given that by construction, my error dynamics are spatially invariant, and already I showed you in the first part of this talk that this gives us a lot of advantages with the Fourier domain. The idea was, could we frame this functional optimization problem in the Fourier domain and see which kind of properties it has? So this is what I did next. So the problem looks a little bit different in frequency, so just let me briefly describe where each of these expressions comes from. So the first one is the cost functional, okay? So what we would like to find is an expression for the steady state variance of those optimal estimation error in the symbols of the operators that we have in our plant, okay? So variances, the symbol of our gain, and the operator A in our dynamics. So we know that we can relate all this to a Lyapunov equation, given that the cost function is quadratic and we have linear dynamics. So we have a Lyapunov equation again at each lambda for this cost. And what this allows me is under the further assumption of scalar Fourier symbols at each lambda, so to solve again for the power spectral density of the error as a function of the Fourier symbols in my dynamics, okay? So this gives me an expression of this form. Now, if something that I want you to realize that is promising, I would say, is that this function here has the form of quadratic over linear in the gain. That is what we are trying to optimize for. And this is something good because we know that these kind of functions are convex in certain regimes of the denominator, okay? Particularly when the denominator is positive. So finally, to recover the variance, that is our cost function, the only thing that we need to do is just apply Gauss-Net formula and integrate the power spectral density. So when we do that, and when we replace this expression in here, we obtain the cost that you see here on the right-hand side. Now, regarding the stability, something that one can show is that in our spatial invariant setting, in L2 spaces with this scalar assumption, the exponential stability of the closed loop is actually equivalent to this condition. So it's equivalent to the supremum over your spatial frequency of the real part of this Fourier symbol to be strictly negative. Okay, so this is the Fourier symbol of your closed loop. So pretty much we equivalently write this here by enforcing this real part to be strictly negative for some small epsilon. And then finally, the constraint that we need to translate to the frequency domain is the compact support constraint. Now, this is a bit funny because in space we have a constraint that is compactly supported, but in frequency, this constraint it's a little bit strange. So how to translate this compact support in a space to frequency? Well, you can just realize that if your kernel is compactly supported, it might satisfy this relationship for all x in the real line, where here this function is just the indicator function of the interval minus tt. So once you have this relationship, what you can do is to take the Fourier transform and apply the convolution theorem to get a constraint of this form. That pretty much is telling you that any function that is compactly supported between minus t and t will need to satisfy a constraint on this form in the frequency domain. And sync here is just a notation for the cardinal sign that is defined in this way. Okay, so this is a function that appears a lot in kind of signal processing and these kind of fields. Okay, so now that we understand where my functional optimization is coming from, let's see if we could say something about the properties of this optimization problem. Okay, so for this I will do something that is to remove actually this compact support constraint just for a little bit. So I know that the whole point of defining this problem is to have this constraint, but I will remove it just for a little bit to derive some properties of this problem, and then I will recover it, okay? And see that some of the nice properties of the problem still hold. So if for a moment I forget or I ignore about its constraint, we have a problem of this form. So pretty much this is saying that I'm trying to solve for my Kalman gain, but optimizing directly on the gain rather than trying to solve a Riccati equation, okay? So what we can observe is that my cost is just a sum over lambda, and my constraints might hold pointwise in lambda as well, the stability constraint. So what this means is that once again, we can use this property of modal decoupling to arrive to a family of optimization problems that is now parameterized by lambda, but that are decoupled in lambda. Okay, so pretty much this is saying that in order to optimize this cost functional, what I need to do is to optimize at each lambda, subject to this stability constraint that must hold pointwise in lambda. So this is what this problem is saying. So I will refer to this problem as the modal optimization problem. And this is now a toy problem where we can really understand a lot of properties. So the first one is this problem is finite dimensional. So I'm trying to optimize for some L hat of t of lambda, you should say. So this is just a complex number. So I'm just trying to optimize its real and imaginary component for a given lambda. So this has it's a problem of very small dimension. The second one is that one can prove that this problem is actually strictly convex in the feasible region. And the way to show that is that you can compute the Hessian of this cost in both the real and imaginary components of this L hat of t at a particular lambda and show that the Hessian is positive definite in the feasible region. Okay, so when you have this stability condition, because the denominator is strictly positive. And with that, you can also show that the optimal solution is actually attained, and that, of course, you recover what you should be recovering, that is the symbol of the Kalman gain, okay? The one that we obtain from the Riccati equation. Now, the nice thing is that this modal convexity, or pointwise convexity, is actually implying the convexity of the original functional optimization problem that I had. So if now I recover this constraint that I ignored earlier, that is my compact Sukor constraint space, this problem remains convex because this constraint is just a linear constraint. The thing that is a little bit nasty is that this constraint is not coupling the whole problem in lambda. Okay, so now I don't have such a nice setting in which I could decouple everything and solve this pointwise in lambda. I will need to solve a bigger optimization problem, but it still remains convex, so we can do this numerically. So let me go back to my simple diffusion study that I mentioned earlier, and let's try to design decentralized filters in this case, okay? So let's try to solve that optimization problem for this case. So the first thing that we start by doing is some dimensional analysis. So the idea is that we would like to group all the parameters in my problem into a single one, and in addition will have physical meaning. So for that, what I do is I rescale all my original variables according to the different parameters in the system, define these dimensionless variables, and then I obtain my diffusion process in dimensionless units, okay? So all the parameters are gone from here. Similarly, I pose the optimization problem that I just showed you in dimensionless variables. So now this capital lambda is the dimensionless spatial frequency. And what I can observe is that in this problem, we do actually have one dimensionless group. So this is the unique dimensionless group or dimensionless parameter that appears in this problem. We know it's unique just by using Buckingham's pi theorem. It tells me how to combine your parameters pretty much and the number of dimensionless groups that you would obtain. And the way in which we define this is as the ratio of the support of your decentralized kernel to the characteristic length scale of the filter that we defined earlier. So the way to interpret this pi star is that in the dimensionless spatial coordinate, so after the rescaling that we introduced here, pi star is representing the support that you are trying to enforce in your decentralized Kalman filter. Okay, so how far you are gathering measurements from. Now, also remember that this L star we defined it earlier is the ratio of kappa to these variances of the noises. Okay, so what this means is that this pi star actually has physical meaning, and what it's capturing is the level of decentralization that we are demanding to our Kalman filter. Okay, so this is something similar to well, Bassam likes to call this the Reynolds number of the Kalman filter. Bassam is one of my good collaborators. So and in some sense, he's right. So the idea with the Reynolds number in general in this kind of complex spatial temporal systems is that you try to define these dimensionless groups such that you have certain behaviors when this dimensionless group takes either a very low value or a very high value. So in the case of the Reynolds number, you have flows that are laminar when the Reynolds number is very low, and flows that are turbulent when the Reynolds number is very high. So in that sense, our pi star will give us similar insights in our problem, in the sense that when pi star is pretty small or less than 1, we are asking for a highly decentralized filter. So we would expect large suboptimality gaps due to going to decentralized architectures of the filter. But alternatively, when this pi star is much larger than 1, but we would expect these low suboptimality gaps, because this is saying now that I'm allowing quite a lot of communications, so quite a large T, as compared as how fast my centralized kernel is decaying, that is dictated by this parameter L star that I defined earlier. Okay, So now that we have this intuition about pi star and the role that it has in this problem, so let's try to actually solve this problem for diffusion. So how do we go about that? Well, we will need to rely on numerics. So the idea would be that we will introduce some finite dimensional approximation of this integral constraint. So we sample and then we introduce some quadrature, okay, in order to approximate this constraint. Then we will plug this back into this cost. And we will do the same. We will introduce some approximation of this integral. So we sample and we do some quadrature of this cost. So what this will give me is a finite dimensional approximation of this problem. So it looks a little bit daunting when that looks at it like that. But the idea is that this is just finite dimensional approximation of this functional optimization. And since we didn't do any strange transformations, the problem remains convex. So we can just plug this into some software like CDX in this case, solve for the kernels and evaluate what kind of behavior we obtain. So if we do that, the first thing to do is to look to the normalized optimality gap. So pretty much this is capturing how much performance am I losing because going to decentralized architectures. So how we define this normalized optimality gap is as the difference between the variance of my decentralized filter, the optimal filter, minus the variance of the so the performance of the Kalman filter, the centralized one, over the performance of the centralized filter. Okay, and we know that this optimality gap will be non-negative because this filter can never, the decentralized filter can never perform better than the centralized one. And thanks to dimensional analysis, once again, what we know is that since this is a dimensionless quantity, it will only depend on this dimensionless parameter that we define pi star, okay? So if we plot that, numerically the behavior is exactly as we expected. So for values of pi star that are less than 1, we have a considerable suboptimality gap around here. And for values of pi star that are pretty large, what we observe is that the suboptimality gap actually goes pretty small. So this is as expected, but I think that the interesting thing here is to actually look at the behavior of the optimal decentralized kernels, okay? So let's start from here. So again, let's remember that pi star, it's denoting the amount of support that I allow this kernel. So if I force pi star to be 0, this means that my kernel will need to be a delta distribution, because we are enforcing the symbol of this kernel to be null infinity. So this must have a delta distribution. So what this would mean is that I'm only using the measurement at a particular spatial location X. I'm only using that measurement from X in order to do filtering. This is why you obtain this delta that, you know, when you convolve this with a signal, you would recover the signal at that particular point. Now, as we start to allow increasing support, so as we allow more and more communications in my decentralized architecture, this is what happens with the kernels. So what we observe is that this delta distribution originally at the origin seems to be splitting in two and going towards the boundary of the support that we allow. And the kernel is growing a continuous component in the middle. Okay, and then as we allow for more and more support, the intensity of these deltas is going down. And in the limit, let's say we would allow to infinite support, and what we would do is to recover the centralized solution. So these kernels are decay exponential in the space. Okay. So something interesting to note is that if we pick one of these optimal compactly supported kernels, okay, and we compare it to the centralized solution, there seems to be some kind of relationship between the two. So in particular, let me plot on top of this one, the centralized kernel. So in black, so this is how the black looks like. So as you can see, there is quite a bunch of overlap between the two solutions. So what it seems is that a pretty good approximation of the optimal decentralized kernel could be simply to truncate the centralized kernel within the supports that I want to enforce in my system, and to add a correction term that is pretty much composed by two delta distributions at the boundaries of my interval, trying to compensate for these missing tails, for this information that I cannot have access to anymore. And then the intensity of these deltas is tuned by this parameter pi star. So in particular, as pi star increases, the intensity of these deltas goes down, okay? So just to summarize, I think this slide is a good summary of the whole talk. So I would like to understand when I could go to decentralized architectures and pretty much have not much normalized optimality gap, as I defined earlier, okay? So by looking at this plot, what you would tell me, well, what you will need to do is to go towards values of pi star that are quite high, above 1. And then you know that if you go to a decentralized architecture, you actually don't have much performance drop. Okay, so if we check again the definition of this parameter pi star, it was the ratio of our support to our characteristic length scale. And if we plug in the definition of our length scale, this is what we obtain. So pi star is a function of course, the support that I allow in my decentralized architecture, but also of the noises and other parameters that I might have in my plant. So what this means is that if I want to make pi star large, an option could be, for example, to increase t. This is sort of the evident option, right? If you want a smaller optimality gap, allow for more communications in your system, and then you should be good to go. The issue is that this t might have an upper bound because you might be constraining the amount of communications that you can have in your system, or by other things like delays, for example, that might be dependent on how far these sensors are. So there might be an upper bound on this t, and you might not always be, it might not always be possible to increase this as much as you want. So what this is telling us is that actually the noises also play a role in when these localized or distributed filter architectures will perform well. So in particular, by improving sensing quality, so by reducing this sigma b, we see that we could increase this pi star and go towards this side of the curve. So, we will be improving our estimation quality, but also we will be localizing more the filter. And then by increasing sigma double b, we could interpret as having high environmental noise, as might happen maybe in biological systems. Localized architectures are also near optimal. Okay, so of course, I'm not saying that it is a good idea to crank up the noise in your system, but the idea here is that given that in some settings you might have some environmental noise that you cannot avoid, in that settings actually might be a good idea to go distributed, because there is not much gain from getting measurements from far away, given that they are not giving you much. Okay, so you could be in this regime pretty much and be performing well. So graphically, this is the intuition. When you are towards this side of the curve, what is happening is that your centralized kernel is actually very widespread in space. You would like to have access to measurements that are far away. So if you fix the support, let's say to be between -2 and 2, and you design the optimal kernel for that support, you see that there is quite a lot of distance, quite a lot of difference between these two kernels. You might expect that you might not perform as well if you go to a decentralized architecture. But as you move in this curve, and if you go towards the other extreme, what you observe is that when this pi star is actually quite large, then your kernels are already pretty concentrated in space. So are pretty concentrated around the support that you would like to have. So if you design now the decentralized kernel that is supported in that desired support, they actually look quite alike. So, you are doing well. So pretty much you're performing pretty well, even if you go to a decentralized architecture. So as a quick conclusion of what I tried to establish today and some related ongoing work. So what I tried to make is a case for the use of these decentralized or localized estimation architectures in noisy continuum systems, particularly when we have distributed measurements in the domain of this system, okay? So first of all, what I did is to characterize the information structures of these Kalman filters and show you that they are spatially localized. And then what we did is further, we established how this spatial localization is actually tuned by the noise and other properties in the plant that might give you some leverage in terms of, for example, sensor selection or the co-design of your plant and your filter in order to achieve good filtering performance while preserving a spatial localization or decentralization. And as a byproduct in this analysis, what I tried to convince you is that this idea of using dimensional analysis is actually a pretty useful idea in systems theory, even though we don't see it very often done. This is typically found in the physics or fluid mechanics literature more than the systems theory. But this idea of actually grouping all the parameters in your plant into dimensionless group is very useful for things like sensitivity analysis, for example, where evaluating the sensitivity to many parameters could be cumbersome. And then in the way, I also define this branch point locus in analogy with the root locus, that it's a useful tool to just by visual inspection of some trajectories in the complex plane, be able to say something about what are going to be the spatial localization properties of your filter and where in which regimes you could perform well by using distributed architectures. So now moving forward, there are a lot of directions I think to follow. All of them would have the ultimate goal of designing optimal decentralized control and estimation architectures for these continuum systems, especially when there is uncertainty on them. So one direction that we are starting now, that is sort of a fun project, starting with a student here at Princeton, is the application of this to crawling locomotion. This is one of the reasons why I was showing you this tiny worm all the time. So this is actually pretty nice. This is how these worms move. This is the propagation of the waves around the body. And this is a pretty cool problem because it requires, of course, breaking the spatial invariance assumption that we had in this talk. It requires nonlinearity. So, you know, it's actually quite fun to try to see how one could design optimal gates, and then how could we use these localized or decentralized architectures to stabilize the system around those optimal gates. So this is a project that is led by Daniel Shen here. I'm collaborating with him in trying to understand the control and estimation of these kind of structures. He's a PhD student here at Princeton, and we are collaborating with the group of Amy Wisa, which has a group on bio-inspired robotic design, pretty much, in trying to actually implement and showcase that these decentralized architectures might be the way to go when we have complex soft systems. But then beyond from that, and more from the theoretical side, I think there are like a lot of interesting directions. So of course, this idea of breaking a spatial invariance, but still, how could you exploit a structure in your dynamics in order to translate these to controllers and then design distributed architectures that perform pretty well. So how to exploit, let's say, symmetries or sparsities in the systems in the controller and estimators. And then, of course, here I assume that the model is known and the statistics of your noise are known, but this is generally not the case. So you would need to, first of all, try to estimate this. So I think there are a lot of interesting directions as well related to uncertainty and risk quantification and the design of risk-sensitive controllers and estimators for spatially distributed systems. So with this, just tell you thank you for staying with me until the end. Happy to take any questions that you may have. And just to acknowledge my advisors here, given that this was the work that I did with my PhD, and to say that if you are interested in related research directions or some of the future directions that I mentioned, feel free to reach out because I'm always happy to have a chat.
Thank you, Juncal, for the great talk. A lot of interesting things. Let's open the stage for questions. You can either type your question in the chat or and I will read it, or you can unmute yourself and ask directly.
Okay, maybe I can get started. Can you hear me?
Yes. Yes,
Okay.
yes, go ahead, Emilio.
I didn't have any reaction. Okay. Well, you know, first of all, you know, thank you, Juncal. Juncal is a very interesting, very elegant work. I really like the connection to the, you know, to the root locus, the branch locus. I always try to put it. So you mentioned that you know, one of the part of the plans is to extend to, you know, like a compact domain, right? And you know, boundary conditions and things like that is very interesting. How about like, for example, two-dimensional domains?
Yeah, so two-dimensional, I don't think it's a problem, or three-dimensional.
Mm-hmm.
Like for example, all the Paley-Wiener theorem goes through, even if you have higher dimensions. Another question is how nasty would be your branch point locus, right? In that setting, that's a different question. But then still the theorems hold, so you would expect the same kind of decays. Now, the more complicated thing is that the decays here are given in an asymptotic way, right? What you can establish is asymptotic exponential decay. So when you have now a finite domain, things become more challenging because you don't have that notion of what is asymptotic. Now, there is the interesting observation is that, so for systems that are, let's say, long but not infinite, what you see is that towards the interior of the system, you have the same decay properties. And then it's towards the boundaries is where actually the decay of the controller change a little bit. So this is where the boundary conditions are actually affecting. So my feeling is that what will happen in that context is that you will have an additional dimensionless group, that it will be now the ratio between your spatial extent, your domain, and the decay rate of these kernels in the spatial invariant setting. And this ratio will tell you how much your boundary conditions affect the controller. So I think pretty much what you could do is to design the controller of the estimator as if it was a spatial invariant, and then add some correction terms towards the boundaries that will account for that lack of a spatial invariance. So I think this is how you could go about it. Yeah.
You know, but wouldn't some of the techniques that you use for the truncated version, for the local version of the filter, apply in that case?
What do you mean by techniques? You mean if the same kernel would work out in that setting, or? I
mean, the same way that you reformulated the problem.
Yeah, okay, but this is the thing. So yeah. So so that relied on the spatial invariance. pretty much, right? So I think if you can do this idea of design a kernel for the spatial invariant setting and then design a correction term for that kernel, I think that will go through. But if not, you don't have that possibility of taking Fourier transforms if you have a domain that is finite, unless you have, of course, something that is periodic, then it will go through. Yeah. So you will need to come up with some alternative ways of doing this. Yeah. Okay. Or adding correction terms, one or the other. Yeah.
Okay. Now, the other thing is that, clearly, this is, for example, when you do the information constraint version, right? So you're really looking at localized information. It's not really the quantity of information, right? So you can.
Yeah, no, definitely. Right? Yeah, definitely. Yeah.
So any thoughts on, finite information in the sense that, for example, you have a finite number of discrete sensors or things like that. So,
so rather than having a continuum,
how would that compare to a discrete version, right? So,
yeah, I don't think it's that. I don't think it would be that different if they are distributed in a space. So you could also think of this problem as having even discrete dynamics, if you want, like discretize it and then say that at each element that you discretize, you have one sensor. So then you would also have this notion of a spatial invariance. It's just that you work with the C transform rather than the Fourier transform. So if you have enough sensors, I think it wouldn't be that far. Now, another question is if you tell me, no, you have a huge domain and you only have 3 sensors. That's a different story. So now you will need to come up with approaches like, sensor placement, or do I want to have, 3 sensors of very good quality versus having more sensors of lower quality, and what overall gives me better performance? But that's a bit of a different question. Yeah.
Okay. Okay. Thank you.
Sure.
Thank you, Emilio. Any other question? I actually have one, related also to the applications you want to look into for the next work. And is so I understand these trade-offs in suboptimality. You also showed this nice diagram at the end. But have you tried getting a sense of the practical implication in one of the examples you look at, for instance, for these soft robots? Or because sure, I agree, sometimes it's bad to have suboptimality, right? But it would be nice to see how does this play a role? Is this just a small refinement in the end for the practical applications you're interested in, or is this actually a crucial thing that you need to get rid of somehow?
Yes, you are talking about the trade-off between local versus global. Is what you are talking about. Yeah. So we haven't implemented this in an actual system, but it's what we are trying to do now with this robot. So the case that we want to establish there is, so we would like to show that, yes, with this local information. So if you think about this robot as being a bunch of modules connecting together, and like this, you build this crawler, and the point would be to now generate these propagating waves. What we would like to show is that just by having communications between your neighboring modules, this is enough and near optimal, pretty much, to propagate this wave. This is what we are trying to show. So that would be, I think, the application where we could showcase this idea. So the idea there would be if you actually implement centralized communication, see how well you could do, and then go to the decentralized version and see that that should be, hopefully, enough and pretty good to preserve this gate and to stabilize this gate. So this is a bit of the idea. Yeah.
Okay, nice. I didn't get that you were already trying to do that. Okay. Very cool stuff. Any other question? Doesn't look so. Well, there is your email address there. I think people can reach out if they have further questions. Thank you very much, Juncal, for the great talk, and also good luck for the next steps. And
thank you.
Thank you all for participating. See you all next week. Bye-bye.
Thank you, Juncal.
Bye.